Hello, my name is Jeffrey, and this is my Physics Lab 5 report. Introduction. The purpose of the lab was to collect data on a barred magnet falling through an aluminum tube to observe and apply Faraday's law, and then to compare the real-life barred magnet with the computer simulation. The physics principles used in this lab were Faraday's law, the Biot-Savart law, Ohm's law, magnetic force equation, and Newton's second law. The equations for which are shown to the left-hand side. In addition, I used a free body diagram to model the barred magnet with gravity pointing downward and magnetic force counteracting it. The main result was that we demonstrated that the magnet's slow descent down the copper tube exemplified Faraday's law. The experimental average time was found to be 1.66 seconds, and the computational time was 1.614 seconds. So for the physical experiment, the system was the aluminum foil tube and the barred magnet, and the surroundings were everything else. The initial conditions were that the bar was dropped straight down from the top, the tube length was 0.35 meters, the tube width was 0.006 meters, the inner radius was 0.019 meters, the magnet's mass was 0.025 kilograms, and the magnetic dipole moment was 3.12. We also assumed that the barred magnet could be treated as a magnetic dipole. For the procedure, we used a magnetometer app to find the north end of the barred magnet, and then drop the magnet through the vertical aluminum foil tube 5 different times, recording how much time passed before the magnet fell through the other side, and then we averaged the times from each trial. The time trials can be shown to the right-hand side, and the average time was found to be 1.66 seconds. We could not have used a ferrous tube because it would have magnetic properties which would attract or repel the poles of the barred magnet, thereby interfering with the data. And the magnet was found to fall slower than it would have without the tube. So for the computational model, this was taken from a template provided from the lab. The main things were that we inputted our initial conditions for the aluminum foil. We also inputted the mass and the magnetic dipole moment of the magnet. Most of this code you see on this slide is from the template. However, the real interesting stuff gets in step 2, where we took our dipole moment equation from lab number 3. We also use a new function to calculate magnetic flux in the bottom left. And then the entire simulation runs from a while loop once everything is initialized. For each iteration of the loop, time is incremented, and it's determined whether or not the bar has entered the tube or has just exited the tube. We also calculate gravity and the magnetic force on the barred magnet. Here you can see the remainder of the while loop to determine all the forces going on, and all these forces play into the calculations for velocity and position of the barred magnet, which continually gets updated from the while loop. On the right hand side, you can see what happens for the simulation at the end of the program. Velocity versus time is graphed, and you can see the graph has a negative slope and then goes up briefly, and then the slope stabilizes before going back down with a negative slope. And the time in the tube in seconds, once again, is 1.614 seconds. So for a comparison discussion, in the simulation, the red, which you couldn't really see because it was the end of the simulation picture, red corresponds to counterclockwise induced current, and blue corresponds to clockwise due to Lenz's law. If the magnet were flipped around, it would have no effect on the system's dynamics, as only the locations of clockwise and counterclockwise induced current would flip. The simulated time was fairly close to the experimental time, but could be closer if more rings were used in the simulation or if other conditions were tweaked. When the velocity versus time graph in the previous slide is flat, magnetic and gravitational force are equal in magnitude, so the barred magnet does not accelerate. But when the velocity versus time graph has a negative slope, gravitational force overpowers magnetic force. The main assumptions in this lab were that the air resistance is considered negligible because the barred magnet is so small and it's not moving anywhere near terminal velocity. And the possible sources of error included incorrect mu value and measurement errors in the real world and routing errors in glow script propagating over time. So if the resistivity of the conductor were reduced as close as possible to zero, the dynamics of the falling magnet would change because due to Ohm's law, induced current would approach infinity as resistivity approaches zero, thereby creating a stronger magnetic force and possibly preventing the magnet from falling at all. If holes or slots were cut into the tube, the induced current would be lower as the holes would break up some of the rings used in Faraday's law. Therefore, the magnet would fall through the tube quicker since magnetic force would be lower.